Good morning, folks. So here we are, another wonderful day of September. And today what we're going to be doing is we're going to be walking into and starting to take a look at what the scientific method actually is and what those steps are that scientists need to take. Going to adjust the camera. There we go. In order to actually come up with good, valid information that other people can make use of. So diving straight in, we're going to get the presentation started in just a moment. All right, so at this point, we should be seeing the presentation. Remember yesterday we talked about the things that we keep in common with the rest of the world in order to actually do science and communicate the information. And we finished with Latin, talking about how Latin is a dead language that therefore does not change. That's really important. So when we say Felis catus, we always know what we're going to be referring to, the domestic cat. We can take a look at scenarios like this, where we've got a Homo sapien and Panthera leo, right? Those words will always mean the exact same thing because Latin doesn't change, unlike English, where words will evolve. They'll mean different things at different time periods, depending on how people use them. We're going to skip this so that I don't get copywritten, but in class we'll see it. All right, so you quite often may hear the idea that it's just a theory. All right, I want everybody to understand very, very clear. A theory in science is not a guess. It's not an idea. In order for something to become a theory, it has to be supported, proven, multiple experiments, tens, hundreds, thousands of them, all have to come to the same conclusion in order for something to become a theory. So for instance, cell theory. Now, I doubt any of you sit there and go, well, cells aren't real, because we can see them. That's just a theory. A theory in biology will never become a law. It doesn't work that way. What happens is a theory remains our best, most evidence-proven approach and belief until something else might come along and change it. That does happen, and we want that to happen. That's a good thing. Otherwise, we would still believe that headaches were caused by evil spirits that get stuck in your head because you yawned when you passed by a graveyard. So just keep this in mind. When someone says in the scientific community that this is a theory, we don't mean it's an idea. We don't mean maybe this is it. We mean that we have a lot of evidence to show that this is the explanation for exactly how things work. We're going to skip this too, but in class, it's a great video if you want to see it. TED Ed, what's the difference between the scientific law and a theory? Phenomenal, and I suggest everybody watch it. I would like to introduce you, though, to Hassan ibn al-Haytham, and I'm probably pronouncing that wrong. This is the father of science. He lived in what is today Baghdad, almost 16-ish hundred years ago. And basically, what he was is he made lenses for eyeglasses, for telescopes, for things like that. And he was studying the way that light behaves. And as all these other people, at that point in human history, Baghdad was the center of science and learning for basically the entire world. Everyone would travel there. That's where the universities were. And Hassan said, you know what? Lots of people are coming in with all sorts of different ideas, and that's great. But they're coming to those conclusions so differently. He said, we need one standard way to make sure that everyone is following the same steps so that everyone is coming to the same conclusion. His quote here, the duty of the man who investigates the writing of scientists, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it so that he may avoid falling into either prejudice or leniency. Basically making sure, is the science good? I don't care whether I should agree with it or not. You need to view it as something that you don't believe. Try to disprove it in every way. And if you can't disprove it, then you have to accept it. That is the basis for modern science. When people talk about climate change and global warming, that is not an idea somebody came up with. It has been attacked from every angle, and it has not been debunked. We need a bunch of scientifically literate people who understand how science works and what it means when scientists come forward and tell you that we need to socially distance because this is dangerous, so that people can behave appropriately, so that people can follow it. See, science is a tool. It's not going to do right or wrong itself. It depends on who's using it and who's watching it. If people watching it can identify that this is wrong, that is very valuable. That can stop bad science from happening. Now, I'm not going to go into who said all of these quotes. Most of you can probably guess. But since 2016, we have seen over 100 environmental law changes come into effect. Now, I can give you a link so that you can see all of these. One of the 100, is good and bad. It has a little bit of positive and a little bit of negative, as it allows states greater control over the control of what toxic substances are released into the environment. For some states, that's good because they're going to be stricter. For other states, it's bad because they're going to be less strict. But this is the goal as the current presidency ends, is to try to get the rest of these in progress pushed through. This is an example of bad science. People who are not listening to what science is telling them, people who are not listening to theory, and this could have disastrous consequences in 10 or 15 years when all of these pollutants have now worked their way into people. So you can't just take it out once it's out there. You have to slow down the release of it and let it break down in nature. All right, so let's get into the main goal today. The ultimate purpose, we've talked about this, is to answer the questions, to explain the world. Important to note, science is not designed to provide evidence to match somebody's expectation. As soon as somebody is saying, well, I want to prove that this is real or this is false, and then they're picking the science that does that, that's not right. That's not how it's supposed to work. It's supposed to work by somebody saying, I want to know what's right or wrong, and then going into it, doing their tests, getting their data, and coming to that conclusion. Now, the steps of the scientific method are pretty straightforward, and you will need to know these. I will be asking you on our first test to fill these in order. So first, define a problem. I gave you an example yesterday where you're walking into school or a store or something, and your foot is kind of scraping or sliding on the ground weirdly. Right there, that's your problem. My shoe's not acting like it normally does. Number two, collect data. So now what you want to do is gather anything that might be relevant to it. Now, in this case with the shoe, that's easy. You take a couple of steps, you feel how it's skipping or sliding or scratching, and you've collected your data. You know that there's something on your shoe that's causing this to behave differently. You know it's probably something hard like a rock. That's all your data. Now you make your hypothesis. You say, there's a rock stuck in the bottom of my shoe. So we're going to make it a little bit more specific, though. We're going to say, well, if there's a rock stuck in the bottom of my shoe, then I should be able to get rid of it on that mat over there. Number four, designing your experiment. So now this must test your hypothesis, not something else. So since my hypothesis was that I have a rock stuck to the bottom of my shoe and the mat will remove it, now I have to go to the mat and actually slide and grind my foot on there in order to try and dislodge that rock. Then we move to the last step. We accept or refuse. So is my shoe back to normal? Yes. Then in which case we can accept our hypothesis. We were right. And now if this were real science, you would try to share it. You want other people to know so that they don't have to spend the time going through the experiment that you did. If I'm wrong and there's still something stuck to my shoe, then you know what? We go back to number two. We know it's not a rock. We know it was not dislodged by that mat, and we try something else. Maybe I stepped on a tack, so now I'm actually going to need to pull it out of my shoe. experiment, pull your shoe up, and you just keep cycling through. It is very important to recognize a hypothesis can be wrong and still be very, very valuable. All right, that's super important. Never be scared about a wrong hypothesis. Even on the Regents, they will ask you, what is a hypothesis this experiment might have been testing? Doesn't matter if the results come up and prove it wrong, it's still a valid hypothesis that was being tested. We're going to have some more work on this in our lab, and you're going to see a second video has been posted today titled Paper Airplane Lab. So from here, you want to go to that one for the explanation of how we're going to do our scientific method lab. I hope everybody understands this. Go back through, take the time that you need in order to get everything written and taken care of. And otherwise, I'll see you in class. Have a great day. And